We are, all of us, made of stardust. This isn't just a poetic phrase, it is a profound scientific truth. The atoms that form our bodies, the oxygen we breathe, the carbon in our trees, were forged in the hearts of stars billions of years ago. To understand ourselves, we must understand the universe. And to understand the universe, we must ask the biggest questions imaginable. What is everything made of? What are the fundamental forces that hold it all together? How did it all begin? For millennia, these were questions for philosophers and poets, but today they are questions for science. And we have built extraordinary machines to find the answers. These machines are called particle accelerators. They are among the largest and most complex scientific instruments ever constructed by humanity. Think of them as time machines of a sort. They don't carry us into the past, but they allow us to recreate the conditions that existed just fractions of a second after the Big Bang. By accelerating tiny particles, the fundamental building blocks of matter, to almost the speed of light and smashing them together, we can briefly glimpse the universe in its infancy. We can witness the raw energy of creation and watch as new particles flicker into existence, revealing the underlying laws of nature in their purest form. The impulse to build these magnificent structures comes from a place of deep human curiosity. It is the same impulse that led our ancestors to look up at the night sky and draw constellations to wonder what the moon was made of, or to ask why the seasons change. It is the drive to explore, to understand our place in the cosmos. These vast rings of magnets and detectors, buried deep underground, are our modern cathedrals. They are monuments to our collective desire to know. They represent the pinnacle of human ingenuity, collaboration, and our unyielding quest for knowledge, pushing the boundaries of what we thought was possible. So, let's take a journey inside these incredible scientific instruments. We will explore their history, understand how they work, and marvel at the discoveries they have enabled. The story of particle accelerators begins not with colossal tunnels, but with humble curiosity and glass tubes in the early 20th century. J.J. Thomson and cathode ray tubes, the ancestors of old TV screens, led to the discovery of the electron. These early devices used electric fields to accelerate particles across short distances. Small enough for a lab bench, they opened a door to an invisible world. The first leap forward, Cockcroft-Walton generators, stacking voltages to give particles a bigger push, leading to the first artificial splitting of the atom in 1932. A monumental achievement. We could manipulate the heart of matter. Next, the cyclotron, invented by Ernest Lawrence in the 1930s. Instead of a single big push, particles got a series of smaller kicks. Magnetic fields bent their path into a spiral, sending them through the same accelerating gap again and again, gaining more energy each turn, higher energies in a compact space. Early cyclotrons fit in one hand, then grew into decades-long workhorses, earning Lawrence a Nobel Prize. They solved the engineering challenge of making particles go faster. As questions grew, machines had to grow. The cyclotron spiral had limits. To go further, we needed a different shape, a ring. Enter the synchrotron, where magnetic field strength rises in sync with particle energy, keeping particles in a stable circular orbit. This unlocked truly enormous accelerators. When you think of a particle accelerator, you are probably picturing the Large Hadron Collider, or LHC. And for good reason. Located at CERN on the Franco-Swiss border near Geneva, it is the largest and most powerful machine ever built by humankind. Its ring is a staggering 27 kilometers in circumference, buried 100 meters underground. The LHC is designed to accelerate two beams of protons in opposite directions to 99.9999991% of the speed of light. Its superconducting magnets, colder than deep space, steer these beams with incredible precision before smashing them together at 4 specific points. These unimaginably energetic collisions reach up to 13.6 trillion electron volts. Their purpose is to recreate the conditions of the early universe and search for new particles and forces. Before the LHC reigned supreme, the king of colliders was the Tevatron at Fermilab near Chicago. For over 25 years, it led particle physics. Its ring measured 6.3 kilometers around. The Tevatron collided protons and antiprotons. Creating and storing antimatter was a fiendish technical challenge. The Tevatron reached nearly 2 trillion electron volts. It explored the energy frontier, hunting for predicted particles. Meanwhile, in Japan, a different kind of collider tackles a different mystery. Super KKB at KEK in Tsukuba is a B factory. It is an asymmetric collider, smashing electrons and positrons at different energies. Its 3-kilometer ring focuses on precision and intensity, not peak energy. Super KKB produces enormous numbers of B mesons. Scientists study their decays with incredible accuracy to hunt for subtle matter-antimatter differences and the reason the universe is made of matter. The 3 colliders represent different strategies. LHC, brute force, highest energies to find heavy particles. Tevatron, pioneering predecessor that charted high-energy territory. Super KKB, extreme precision and a flood of data for indirect clues. Together they form a global network of discovery, each probing the cosmos in unique, powerful ways. While giant colliders smash particles together to break them apart, another type of accelerator uses the light that particles produce to see things in breathtaking detail. These are the synchrotrons, or synchrotron light sources. Instead of colliding, a beam of electrons is accelerated to near the speed of light and guided around a large storage ring by powerful magnets. Every time a magnet bends the path of these high-speed electrons, they radiate intense beams of light, ranging from infrared to X-rays. This isn't just any light, it's millions of times brighter than the sun. This brilliant light is then channeled down beamlines to dozens of experimental stations simultaneously. One of the world's leading facilities is the European Synchrotron Radiation Facility, or ESRF, nestled in the French Alps in Grenoble. With its 844-meter circumference ring, the ESRF produces some of the most intense and energetic X-rays on the planet. This supermicroscope allows scientists to study the structure of matter at the atomic level. Biologists use it to determine the intricate shapes of proteins and viruses. Materials scientists can watch how alloys form and how batteries charge and discharge in real time. Archaeologists can even peer inside ancient fossils and reveal hidden text on fragile manuscripts without ever touching them. In the United Kingdom near Oxford lies the Diamond Light Source. This state-of-the-art synchrotron, with a circumference of over half a kilometer, serves thousands of academic and industrial researchers every year. Its powerful X-ray, ultraviolet and infrared beams are used for an astonishingly wide range of applications. Scientists at Diamond have developed new catalysts for green energy, designed more efficient solar cells, and investigated the molecular mechanisms behind diseases like Alzheimer's and COVID-19. Further across the globe, the Australian Synchrotron in Melbourne provides similar capabilities for the Asia-Pacific region. This 216-meter ring is a vital piece of national scientific infrastructure. Its beamlines have been used to improve the taste of chocolate, develop longer-lasting paints, and help design advanced manufacturing processes for the aerospace industry. On the 4th of July 2012, the world of physics changed forever. In a packed auditorium at CERN, scientists from the LHC experiments announced the discovery of a new particle. It was the Higgs boson. For nearly 50 years, this particle had been the missing cornerstone of the Standard Model, the theory that describes the fundamental particles and forces. The Higgs field permeates all of space and gives fundamental particles their mass. Without it, particles would fly around at the speed of light, and atoms, stars, and galaxies could never form. Finding the Higgs boson was a monumental triumph of theory and experiment, a Nobel Prize-winning discovery that confirmed our understanding of the universe. Years earlier, in 1995, a different kind of discovery electrified the community. At Fermilab's Tevatron, after a long and arduous search, 2 competing experiments finally found the top quark. The Standard Model predicted 6 types of quarks. 5 had already been found. The top quark was the last, the most massive, the most elusive. Its mass, about the same as an atom of gold, required the highest energy collisions. Its discovery was a crowning achievement for the Tevatron, completing the picture of the fundamental building blocks of matter. Beyond quarks and bosons, accelerators shed new light on the neutrino. These ghostly particles barely interact, streaming through us by the trillion every second. Accelerator experiments create intense neutrino beams at facilities like T2K in Japan and projects at Fermilab. They confirmed neutrino oscillation, changing type as they travel. That proves neutrinos have mass, hinting at physics beyond the Standard Model. The impact goes beyond fundamental physics. Bright X-rays from synchrotrons revolutionized medicine and biology. They helped determine the structure of the ribosome, the cellular machine that builds proteins, earning a Nobel Prize. During COVID-19, synchrotrons worldwide, Diamond, ESRF, and others, mapped the SARS-CoV-2 virus and its spike protein. That work enabled rapid vaccine and antiviral development. From the biggest questions about the cosmos to urgent challenges in human health, these accelerators have delivered moments that have reshaped our world.